Okay, so thanks very much for inviting me. I'll describe the goals of this talk on the next slide. I want to develop algorithms and hardness results for classical linear algebra problems. This talk is based on a few works with Ken Clarkson and also interesting discussions that I had with Amir Aboud, Yuqing Ai, Arthur Speckers, and Richard Peng. There's a part of the talk that is still like work in progress, and that's what these discussions are about. Sort of the status is we have many algorithms for and reductions between graph problems, string problems. We've seen a lot of problems in this workshop, such as all pair shortest paths, finding triangles, etc. And the goal of this talk is to ask the question is, can we do the same thing for linear algebra problems? Okay, so what are some problems that that people study? So some classical optimization problems. One is regression. So given an n by d matrix A, typically n is much larger than d. It's a tall, thin matrix. And an n by 1 vector B. Find a vector x which minimizes the norm of ax minus b. Okay, where you can look at various different norms. If I take the Euclidean norm, this is the least squares problem. So ax gives you the closest vector in the column span of A to b. So this is in polynomial time, but how quickly can you find such an x? Another question is low-rank approximation. So given an n by d matrix A and an integer parameter k, output a rank k matrix B, which is as close as possible to A under some norm. Okay, and we'll look at a few different norms in this talk. You could ask even more basic questions. So what is the complexity of the following problems? Suppose I'm given a symmetric n by n binary matrix A, and I want to output an additive 1 over poly n approximation to each of its eigenvalues. Okay, so it's symmetric, it's n by n, it's binary, so you have bounds, you have worst case bounds on the eigenvalues. What is the complexity of this problem? So the output description here is just n log n bits. Can I do it in linear time to describe A? You could also ask a relative error version of this. Given an n by n matrix A and an integer k, what if I want a multiplicative 2 approximation to its kth singular value? So here the output is really tiny, right? It's just a 2 approximation to a number. And we call the singular values of the square roots of the eigenvalues of A transpose A. So what is like a complexity of this problem? Okay, so the outline of the talk is as follows. I'll first show how you can solve a number of linear algebra problems in time which is proportional to the time just to describe the input. So we shouldn't have hardness. And these come by reduction. So what they do is they take, say, an instance of regression, and they reduce the problem very quickly in input description time to a smaller version of itself. Okay? And this is what I like to call like a sketch and solve paradigm. So I'll go over low-rank approximation, and then variants of that, robust low-rank approximation. And then the second part of the talk is more, sort of work in progress. So it's a notion of low-rank approximation called spectral low-rank approximation. And here I think there should be a hardness. Okay. So let me just go over low-rank approximation. You're given an n by d matrix A. And think of the n rows of A as being points in Rd. For example, A might be a customer product matrix, and Aij might indicate how many times customer I purchased item J. In many cases, A is well approximated by a low-rank matrix. Okay, so it might only be high rank because of noise that was added to the system. And so the goal is to find a low-rank matrix approximating A. It's easy to store a low-rank matrix in factored form. It can make your data more interpretable, etc. Okay, so what is a good low-rank approximation? So we call the singular value decomposition the SVD, that any matrix A can be written as the product of three matrices U, sigma, and V, where U has orthonormal columns, sigma is diagonal with the entries are decreasing as I go down the diagonal, and V has orthonormal rows. Okay. So one way of getting a low rank approximation, say a rank K approximation, is just to truncate this diagonal matrix sigma. Okay, so I take the top K entries of sigma, I leave them alone, and I zero out the remaining entries. And this corresponds to selecting the K leftmost vectors of U and the K uppermost vectors of V. That's a rank K matrix. And so I approximate A by this, and I get some error matrix here. So why do that? Well, oh, by the way, so the rows of VK here are called the top K principal components. So why do that? Well, this matrix, this rank K approximation, denoted A sub K, is actually the best rank K approximation to A under many different norms. In particular, under the Frobenius norm, just the entry-wise Euclidean norm of the matrix. Okay, so this is the optimal solution, and the SVD can be computed in polynomial time, in particular in the minimum of nd squared and n squared d time. You can do a bit better with fast matrix multiplication, but still it's quite expensive. Okay, so we really want algorithms, or we either want an algorithm which runs in time proportional to the time of describing the input A, or we want to maybe have some conditional hardness for such a problem. So it turns out that if you relax the problem by allowing for approximation, so now I output a rank K matrix B so that the norm of A minus B is at most 1 plus epsilon times the best possible, then actually you can do much better. And you also allow a tiny probability of failure. You can get a running time which is number of non-zero entries of A, n and z of A, plus a typically lower order term, so n plus d times polynomial and k over epsilon. Okay, so k is the rank parameter, is typically not too large. 1 over epsilon is also typically not too large. So here this is really an input sparsity time algorithm up to these low order terms. This was the technique was sort of a sketch and solve technique which was pioneered for this by Sarlos, and we were able to get better running time with Clarkson. So let me give you an idea how to achieve this running time for approximate SVD. So the idea is as follows. So you're given this n by d input matrix A. You think of having these endpoints in RD. And the first step is what you do is you compute S times A. Okay, where S is a random matrix. There are many different kinds of random matrices S that work. I'll go over some of those. I'll call this sketching matrix S. And S, what it is it's a very wide fat matrix. Okay, so it has k over epsilon rows and n columns. And so what S times A is doing is it's taking k over epsilon random linear combinations of the points, these n points. And I can look at the rows of S times A as a subspace in RD, which I've drawn here as a line. And the next step of the algorithm is to take the n points, the rows of A, and project them onto this space, S times A. Okay? So I project them the closest point in S times A, and now what do? I do the SVD in this lower dimensional space. Okay, so I had these endpoints in RD. We said the SVD was very inefficient. What I'm going to do is project them onto a very low dimensional space, and then now I can afford to compute the SVD exactly, because the dimension is k over epsilon, so it'd be like n k over epsilon squared time. So let me. So the first natural question is which matrices S work so that if I do this procedure, I'll get a 1 plus epsilon approximation. One natural family of matrices is just a matrix of IID normal random variables. Okay, if I choose k over epsilon rows, then you can show that if I do this procedure, I'll get a 1 plus epsilon approximation. Okay, but there's a problem with choosing such an S. Okay, yeah, so the problem is that S is a very dense matrix. So computing S times A itself won't give you time proportional to the time to describe the input. Okay, so in a very nice paper of Thomasarlos, he showed that instead S can be a k over epsilon by n Fast-Johnson-Lindenstrauss matrix. Okay, and this uses algorithms for FFT. So now actually you can compute S times A in time which is roughly n times d. Which is, up to a log n factor, which is optimal for dense matrices. However, it's still not, input description time. This method can't exploit the fact if your input matrix A is sparse. So what we showed is that instead, if S is a poly k over epsilon by n count sketch matrix, then this approach, this sketch and solve paradigm using this S still works. So here the number of rows is slightly larger. Think of poly k over epsilon as being k over epsilon squared. But still this goes into the lower order term. So the nice thing about this count sketch matrix is that it's very sparse. Okay, so what it is so I have these n columns, and in each column I have a single non-zero entry chosen at a uniformly random position. And I put 1 or minus 1 on that location or with equal probability. Okay, so the point here is that S times A can now be computed in input sparsity time. Yeah?
So why do you call this a count sketch matrix?
Oh, why is it called that? Because...
anything in particular, or is it...
No. It's just it's a matrix that's used in the data stream literature, and it's... So it came from the data stream literature, and what they're doing is estimating heavy items. They're counting these things.
So you just have something with mostly zeros and then a few pluses and minuses.
Yeah, so to say it again, like each column independently, you have a single non-zero entry. And on that entry, you put 1 or minus 1 with equal probability. Okay. Yeah. And so S times A can be computed in n and z of A time. Yeah? That's good? Okay. Let me go over the current algorithm for low rank approximation because there's still a caveat. So what did we say we're going to do? We're given this n by d matrix A. We compute S times A. Using the count sketch matrix, we can do this in input sparsity time. The next step we said is let's project each of the rows, the n points of A, onto S times A. So it's not clear how to do that in input sparsity time. Let's get back to that. And the final step is once all these points, these endpoints are inside of S times A, now we can afford to do the SVD inside of that low dimensional space. Okay? And so this is efficient. This is like n times poly k over epsilon. Okay, so yeah, the bottleneck is step 2. So how do you project these points onto S times A? So what we can do instead is we can approximate this projection itself. So, and for this we use a fast algorithm for approximate regression. So let me just recast the problem as follows. So what the theory is guaranteed is that the space, the rows of S times A contain a good k-dimensional space in their span. So I know that if I solve this optimization problem, the minimum over rank k matrices X of the norm of X times SA minus A, I'll get a good rank k approximation. But why should I solve this exactly? I mean, this is an instance of regression. I can solve it using approximate regression. Right? So I already know that if I solve for the optimal X, I'll get a 1 plus epsilon approximation. And if I instead get an approximation to this, I'll get a 1 plus epsilon squared approximation. Okay, so that's the idea. To find this approximate solution, it's a reduction of a regression problem to a smaller instance of regression. So we instead output this x prime, which is rank k, and so that the cost of x prime SA minus A is at most 1 plus epsilon times the optimal cost. And we do it in much the same way. So we choose a random matrix, call it R, which will be a count sketch matrix. It's D by poly k over epsilon. So we're going to be multiplying on the right, so it's D by something small. We take our space S times A, and we compute S times A times R. We take A, and we compute A times R. And now we instead solve this much smaller instance of regression. Okay? So what we do is we've replaced SA with SAR and A with AR. And now we find the x prime, which minimizes this expression. Okay, and let me mention that if R is this count sketch matrix, you can compute S times AR and A times R in number of non-zero entries of A time. The reason is that SA, the number of non-zero entries of SA is also at most the number of non-zero entries of A. So this can all be done efficiently. And now that you have a small problem, you can actually solve this exactly in n times poly k over epsilon time. Okay? So just to summarize, the overall time for low rank approximation is input sparsity time plus n plus d poly k over epsilon. Okay? Any questions about this? Okay. Okay, so let me move on now to robust low-rank approximation. Here we have both input sparsity time algorithms, and we have hardness, conditional hardness, assuming ETH. So first, what is the problem? So this SVD is a little bit sensitive to outliers, right? So we have these n points in RD, and we're trying to find a low-dimensional space which minimizes the sum of squared distances to it. If we have one point which is a little bit further away, since we're squaring these distances, we actually have to pay a lot of attention to it. And so then our space sort of shifts towards that point, and we capture less of this, less of the remaining low-dimensional structure. So a natural thing to do, is try to come up with a more robust cost measure. What's one property you might want of this measure? So one is that if you take your endpoints in RD and you rotate RD, that the cost is preserved. Right? It seems like you might want something that only depends on the geometry of these points, as opposed to penalizing for some particular basis that you might choose. So if I have this rotation matrix W, and I get these rotated n rows of A, I want the same cost. So what's a natural cost function that generalizes the SVD? Well, it's the following. So, one of them is the following. So instead of finding the best k-dimensional space, which minimizes the sum of square distances, I minimize the sum of pth powers of distances of my points to a subspace, where p is a parameter. And note that this is rotationally invariant. I mean, these are Euclidean distances. If I rotate the space, this cost function is preserved. The nice thing, though, is that if I choose p to be less than 2, this is more robust than the SVD in the sense that I described. Right? So I'm not squaring these distances. In particular, for p equals 1, it's a question that might even be arguably more fundamental than the SVD. I'm just trying to find a subspace which minimizes the sum of distances of my points to that space. Okay? Okay, so what is known about this? So just let me say notationally, so 1 plus epsilon approximation for a space V prime means if I plug it into this objective function, I get 1 plus epsilon relative error. So what's known for any p at least 1, I can find a 1 plus epsilon approximation in time which is n times d poly k over epsilon plus an exponential term in poly k over epsilon. Okay, so the first thing that might strike you is that there's an exponential term here, and is it necessary? Another thing is the leading, if k and epsilon are small, or k over epsilon is small, this leading order term, we might also want input description time as opposed to nd poly k over epsilon. One way of handling this exponential term is to relax the problem and instead output what's known as a weak core set. So all this is saying is instead of outputting a k-dimensional space, which is a 1 plus epsilon approximation, I output a slightly larger dimensional space. Okay, so I output a poly k over epsilon dimensional space, which contains a good k-dimensional space in its span. We just don't know how to find it. If you allow this relaxation, then you can get rid of this exponential term. So this exponential term is really coming from the fact that you don't know which k-dimensional space to choose inside of this weak core set. So you can get n times d poly k over epsilon. You still might want input description time. For p greater than 2, which is not the focus of this talk because this this doesn't correspond to a robust version of the SVD. This is actually making the powers larger. The problem is NP hard to approximate up to a fixed constant factor depending on p. This is work by Deshpande et al. And Guruswamy et al. And there's a nearly matching constant approximation factor polynomial time algorithm. Okay, so our results for this problem, what we show is that for any p less than 2, there is an algorithm which achieves input sparsity time plus n plus d poly k over epsilon plus this exponential term. And actually this exponential term we will show is necessary. I'll mention in a second. So if you just want a weak core set, you can get rid of the exponential term, and then you'll get a running time which is very similar to what it was for the SVD. Okay, so input sparsity time plus n plus d poly k over epsilon. What we show is there is, assuming the exponential time hypothesis, there is an n to the k time lower bound if epsilon is 1 over d. Okay, so what this means is, interpreting this, you can't actually get an algorithm which is polynomial in all of the parameters, n, d, k, and 1 over epsilon. But we don't know if the problem is still hard if epsilon is a fixed constant. So that's an open question I'll mention again later. But at least, it suggests that I can't sort of completely get rid of this exponential term. We can generalize this to a large class of low-rank approximation problems. Instead of finding a k-dimensional space which minimizes the sum of pth powers, you can imagine sort of general functions of your distances. And for a class of functions, we can get similar running times. I'll just briefly go over the algorithm for the case of p equals 1 when I'm taking the sum of distances. Okay, so let's try to follow the intuition that we had for the approximate SVD, getting this input sparsity time. The first step was to try to get a low-dimensional space which contains a good k-dimensional space inside of it. This makes all the computations more efficient. So for the SVD, we just computed S times A, where S was a random matrix. We don't have such a thing for sum of distances. Okay, we don't have a distribution on random matrices, which, or we don't know of one, which gives us similar properties. So we don't really have this first step. What we do have is the following statement, which is a statement of the following form. So there's a set of probabilities, P1 through Pn, such that if for each of the n rows of A, these n points, I independently decide to include each row in a sample with that probability. So I include the ith row with probability pi. Then the sample set I get will contain a good k-dimensional space in its span. Now there are some caveats. First, the sum of these probabilities is polynomial in k. So the expected number of samples I'll get by this procedure will be polynomial in k. Moreover, the guarantee is not that this space that I get contains a good 1 plus epsilon approximation. The guarantee is that it contains a much cruder poly k approximation. But we'll be able to bootstrap given such a coarse approximation. So there exist these probabilities. So what? We want to do this fast. So the time to find these probabilities, the previous best algorithm was n times poly d, okay, which is not so exciting. So it turns out that we'll use sketching, again, this, reducing the problem to a smaller instance of itself to find these probabilities much faster. So let me just give you an idea for the overall algorithm. So the first step of the algorithm is to replace A with A times R, okay, where R is a count sketch matrix. This reduces the matrix from being n by d to n by poly k over epsilon. Okay, and now we said we need to find these probabilities, and the time was like n times dimension to the fifth, or I didn't say exactly what it was, n times polynomial in dimension time. Now what do you imagine the next step is? So the next step is, instead of creating these probabilities based on A, we create these probabilities based on A times R, where the dimension, the number of columns of A times R, is much smaller. These probabilities, by the way, if you've seen it before, they're called the L1 leverage scores. I mean, just a term to keep in mind. But this step is now efficient. So now I can create these in n times poly k over epsilon time. And now what did we say the next step was? Once we have these probabilities, we can sample. So we sample the rows of A according to these probabilities that we found from A times R. And we get some sample set S, which was a very crude approximation, if you remember. All we said is it contains a poly k approximation in its span. But now there's a bootstrapping procedure called adaptive sampling, which is we're going to additionally sample more rows, more points of A, as follows. We're going to look at each of the rows, and we're going to compute its distance to our current sample set. Okay, so P sub S here means the projection onto the current sample set. And so for a given row, AI minus AI PS, that Euclidean norm is the distance to my current set of samples. And intuitively, we should be sampling points with higher probability the further that they are away from this space. Sort of these are the points that we're not capturing so far. And this works. So if I additionally sample a set T of poly k over epsilon rows of A proportional to their distance to the crude sample set, then actually I can guarantee that now this new set, S union T, will contain a good 1 plus epsilon approximation. Now you might be wondering, how do I actually compute these probabilities? As we said, it's not efficient to project all of these points onto a space. Well, we do the same kind of thing as before. Okay, so we approximate each of these residuals, again using sketching. Okay, so we can set up these kinds of regression problems, as I said, that we did for the SVD. And so we can, in input sparsity time, actually find the sample set. And finally, the last step is the step where the exponential in k over epsilon term comes from. So once you have this set, your crude samples S and your adaptively chosen samples T, you need to find the best k-dimensional space inside of the span of the union. So one way of doing this is to set up a system of polynomial inequalities and run a generic polynomial system solver, and that gives you an exponential in k over epsilon time. However, as I said, if you don't like that term, you can stop at step 4 if you just want a weak core set, because at this point, you're guaranteed that S union T contains a good k-dimensional space in its span. Okay, so that's the idea here, and the same basic framework applies to these other loss functions, and the overall time is input sparsity time plus n plus d poly k over epsilon plus an exponential term for the last step in k over epsilon. Any questions about this algorithm? Okay. Okay. So so let me now move on to spectral low rank approximation. And here, this is just some discussions and some some questions that I have for this community. So first, so unlike these forms of low rank approximation, we don't have optimal algorithms. So returning to some of the questions in the beginning, the first question is that I had is, how much time is needed to output simultaneously for every I an approximation EI to the ith eigenvalue of A, say up to additive 1 over poly n? Yeah.
A was a symmetric n by n matrix.
Yeah, sorry. A is a symmetric n by n matrix, yeah.
Were the constraints from the input?
Let's say it's a binary matrix. Yeah.
So zeros and ones.
Yeah. So, I mean, this is a, so I like, what are some conditional lower bounds for this problem? Any suggestions? I mean, so I think these problems might be very canonical for linear algebra. So here's, something that is just something. So suppose I take A to be an adjacency matrix of a graph, and I had all of these approximations EI for each of the eigenvalues. Then what is the trace of A cubed? This is the sum of the cubes of the eigenvalues. And what else does the trace of A cubed indicate? Well, it indicates I can count the number of triangles in the graph. And what is the best known algorithm we have for counting triangles? I mean, even if matrix multiplication is exponent is 2. So basically the best known algorithm I know is n in z of A to the 4/3, right? So this is saying something that, yeah, I mean, so, but maybe there's something much better here. And maybe you'll solve it in the next 10 minutes. Let me know. Another question is, I had this relative error question. So given an integer value k, how much time is needed to output a number e, which is a 2 approximation to the kth singular value of A? Let's say the entries of A are, again, bounded, maybe 0, 1, minus 1. Any ideas, like, how hard this problem is? And this is actually an important problem because the spectral low rank approximation actually can be used to solve this problem. So, and I'll get to the definition of that in a second.
Sorry, I think I missed. What is sigma k?
Oh, sorry. Yeah, so sigma k is the kth singular value of A. So it's the kth. So I take A transpose A, and I look at its eigenvalues, and it's the square root of the kth eigenvalue. Any ideas on this? Like, should this be a hard problem? Okay, so here's one thing. I mean, it's just something. I wouldn't call it a solution. It's definitely not. But let's say I take A to be the Tut matrix of a graph on k nodes. Okay, so do you remember the Tut matrix? Like, okay, so it's like the adjacency matrix, but instead of, if I have an edge between I and j, I don't have a 1 and a 1 in the I, j, and j ith entry. I have a 1 and a minus 1. Okay, well, if I take the Tut matrix of a graph on k nodes, then if I had such an E, such an approximation, I could determine if that matrix was full rank, right? Because I'm distinguishing between 0 and non-zero. And the graph has a perfect matching if and only if the rank of the Tut matrix, if it's a full rank matrix. Okay, so these are like some, and the best known algorithm for this matching problem is the minimum of n in z of a times root k and n in z of a plus k to the omega time, which gives some kind of superlinear lower bounds when k is large. But I mean, this is basically just saying that computing the rank of a matrix, we don't have is hard. Like what I'd really like to understand here is maybe not distinguishing 0 from non-zero, but distinguishing a positive singular value from twice that value. Okay, so let me just say what spectral low rank approximation is, what the open question is. So suppose A is an n by n matrix. Now I want to find a rank k matrix B for which the operator norm of A minus B is small. Okay, so remember the operator norm of a matrix is the supremum over unit vectors of the length of a matrix C is the length of C times X. So this is the largest singular value of A minus B. So now what I want is this to be at most 1 plus epsilon times the k plus first singular value of A. Okay, so let me just say that I'm approximating A by a rank k matrix B. The best thing to do would be to choose B to align with the top k singular values of A, and then I would get error, which is the k plus first singular value of A. And now I'm relaxing that problem and asking you for a 1 plus epsilon approximation. Okay, so and this can give much stronger guarantees than Frobenius norm low rank approximation. Imagine if my matrix is diagonal and it has a 2 and a bunch of 1s. Okay, then there's no really good rank 1 approximation in Frobenius norm, because since I have so many 1s, like 1 plus epsilon times this tail, I can just output the 0 matrix for a low rank approximation with respect to those earlier cost measures that I discussed. But for this spectral low rank approximation, I really need to notice that there's a 2 here. Okay? Because I really need to reduce the operator norm of this matrix from 2 down to 1 plus epsilon. So this is just an example where it's much more powerful. Okay. So what is known about this? How do I compute a spectral low rank approximation? So the algorithm, is classical. It's just the power method. But since we're computing a rank k approximation, it's k-fold power method. So let me say what that is. So let q be log n over epsilon. It's the number of iterations of the power method. You compute a matrix B, which is G times A to the Q, where G is a k by n matrix of IID normal random variables. Okay, so how do you compute this? Well, you first compute G times A, and then you get a new k by n matrix. Then you compute G times A, and you do that Q times. Okay? And it doesn't matter if you choose, say, like a count sketch matrix or some other faster matrix G here, because after you run this a few steps, the matrix is going to become dense, this k by n matrix that you're carrying along. The guarantee is you can show that at the end you get this k by n matrix B, and the rows span a 1 plus epsilon approximation to the best spectral low rank approximation. The time is k times n in z of a times log n over epsilon. So what I want to know is if k times n in z of a here is necessary or not. Okay, for these other versions of low rank approximation, we just got n in z of a time. So one thing that Arturs and Amir pointed out to me is if your matrix is dense, then actually you can use yeah.
What happened to Q in that formula?
Oh, it's k times n in z of a times q.
Oh, sorry. Okay.
Yeah. I mean, for this talk, like Q, think of it as like not important. So one thing that was pointed out to me is that if k is not too large, say less than n to the 0.3, then there is an algorithm that runs in roughly n squared time. And it proceeds by doing this algorithm, but at each step using fast rectangular matrix multiplication to do the matrix multiplication, okay? Using, say, Coppersmith or Legal's improvement. Okay, but in general, so in general for dense matrices, this is not that far off from the best possible, right? For sparse matrices, we still don't know anything better than Kn and Z of A, or much better. There was very nice work by Musco and Musco, which improved the epsilon dependence to root epsilon. But yeah, in general, the question is, can we achieve input sparsity time plus n times poly k over epsilon for this problem, like we could for the other low-rank problems? And I should mention there is a reduction. You can reduce this problem in n and z of a plus nk time to the problem of approximating the kth singular value of a matrix. Okay, and how hard is that problem? Should that be a canonical problem? Okay, so yeah. Okay, so let me just conclude. So hardness in P for a number of linear algebra problems does not seem very well understood. We saw that for some classical problems you can actually get optimal input sparsity time for Frobenius norm error and some robust versions of low-rank approximation. Some open questions that came out of this. So robust low-rank approximation, as I said, we don't know if the problem is in polynomial time for fixed approximation error and growing k, the dimension of the subspace. For spectral low-rank approximation, is there a conditional lower bound, say of n and z of a times k, when your matrix is, say, order n sparse? I have a recent monograph with a lot of this material if you're interested, and that's all. Thank you.
Time for questions?
Yeah.
That problem that you said can count the number of triangles in the graph.
Yeah.
What was the upper bound for it that is known?
The best known algorithm for counting the number of triangles, or the problem for that. You mean just the problem of estimating each of the eigenvalues up to? Yeah. So in general, it's basically this SVD time. So yeah, it's much higher. Yeah.
Any other questions? All right, so let's thank David.